Hi everyone and welcome to another Chemistry Academy video. Today we are going to be looking at collision theory and reaction pathways. So this is the introduction to controlling the rate of a reaction in higher chemistry, and we are just going to focus on the collision theory and reaction pathway stuff in this video. If you're looking for the effects of different factors on rates and relative rate calculations, you can check out my other video for that. So for a reaction to occur, the particles need to collide successfully. Successfully is the key word when it comes to higher. In National 5 you tend to just talk about collisions, but we don't talk about whether they are actually successful or not. In order for a collision of particles to be successful, two requirements need to be met. So they are that the particles must collide with sufficient energy to overcome the activation energy. So the activation energy is the energy they need to achieve to start the reaction. So they need to collide with sufficient energy to overcome that. Trying to use the word sufficient and not the word enough, because enough seems to be a bit too ambiguous. And then the second requirement is that particles must collide with the correct geometry. So what that means, I'm going to grab a couple of board pens. So molecules tend to react at their functional groups. So let's just say the tips of my black pens are the functional groups. The particles will need to collide with the functional groups meeting and not like this. So that would be the incorrect geometry where the functional groups aren't next to each other. That could be an example of the correct geometry. Or you can use the word orientation instead if you would rather. Okay, so two requirements. Particles need to collide with sufficient energy to overcome the activation energy, and they must collide with the correct geometry or orientation. So once they collide successfully, they will then be converted into products. But there is an intermediate that the molecules pass through on their way from being reactants to becoming products, and that is something called an activated complex. So the activated complex is basically just where the bonds in your reactants start to break and the bonds in your products start to be made. So it's essentially just a transition period. When we're looking at potential energy diagrams for reaction pathways, the activated complex will form once the particles have reached the activation energy. So that's this like energy hill that they need to climb. So remember I said the activation energy is the energy you need to start the reaction. So our reactants energy, just as they're sitting, is around about here, say. They then need to achieve this much energy to get to the top of this energy hill, and then once they've formed an activated complex, they're then converted into products, and then this is the energy of the products. So I'll put a wee R here for reactants and a P for products. Okay, so these are reaction pathways for two different reactions. Now, there's information you need to get, you could be asked to retrieve from these potential energy diagrams for reaction pathways. So there will be numbers at this scale normally. So let me just label some numbers on. So let's just say that's 50 and this is 100. And then here we'll do 50, and then we'll say that's 120 up there. So we have, like I mentioned already, the activation energy. So that's the energy hill that the particles need to climb to successfully overcome the activation energy. So the forwards reaction, we'd be starting down here at 50 kilojoules and we need to climb up to 100. So that means the activation energy is plus 50 kilojoules in this case, because the particles need to gain 50 kilojoules of energy from where they've started in order to get to the top of that hill. So that would be plus 50 kilojoules per mole. We've then got this delta H here, so that stands for enthalpy change, and that's just the energy change within the reaction. So the enthalpy change is just the difference between the energy the reactants have versus the products. So I always think of it as like taking money out of your bank or putting money in your bank, as it sometimes might be. So it's basically the difference in your balances, the difference in the two levels. So I've not labelled a number here, but let's just say this is 20. I can fit it in. So our reactant's energy are at 50, the products are at 20. So that means we've gone from 50 down to 20, so that's minus 30. So this is where it's helpful to think of it as a bank balance. So you started with £50, you finished with £20, that means you must have taken £30 out, so it's negative. When the enthalpy change is negative and you've taken energy out of the reaction, that's an exothermic reaction. So that's the ones that get hot when you touch them, but energy is released to the surroundings in an exothermic reaction, and that's why it's a negative enthalpy change, because energy has been given out. Okay, so that's for the forward reaction. If you were asked to do the same thing for the backwards reaction, you just want to climb the hill the other way around. So our products are starting at 20 and they need to get up to 100. So that means for the reverse reaction, the activation energy would be 80 kilojoules. I'm going to get a different coloured pen. So starting down here, we need to go all the way up to the top. Okay, so the activation energy for the backwards reaction would be from 20 up to 100, so that would be 80. So plus 80 kilojoules per mole. And then the enthalpy change, so it's going from 20 up to 50 this time, which means that it's like putting £30 into our bank. So for our backwards or reverse reaction, the enthalpy change would be plus 30 kilojoules per mole. Okay, so just think of it as sort of like a bank balance and then a hill that you need to climb, and it does make it a little bit easier to interpret them, especially when you're looking at it for the backwards reaction. That can sometimes be the hardest one to look at. So if we have a look at this graph now, so it's very similar, but there are some differences. So if we were to look for the activation energy, we've started at 50, we're going up to 120, so that means you would need to add 70 kilojoules, so the activation energy here would be 70. The activated complex again would form up here at the top, and then the energy for our products, I've not written on a number, so let's just say that's 80. So that means that the enthalpy change, the difference between our two levels, we started with 50, we've now ended up at 80, so that would be plus 30 for the forwards reaction. Because it's positive, that's an endothermic reaction, so if you're adding energy into the system, into the reaction, that's endothermic. So it's like putting money into your bank. And they're the reactions that feel cold when you touch them because the energy is being absorbed from the atmosphere, so it takes in the heat. So, okay, if we were to do this for the backwards reaction, our activation energy, we're going from 80 up to 120, so that would be plus 40. And this time, for the enthalpy change, we're going from 80 down to 50, so that would be minus 30 for the backwards reaction. Okay, so just think of it, like I said, as a hill you're trying to climb, and I would definitely also use your finger when you're trying to work out the values, just so you don't get confused. The last thing is what happens to these reaction pathways if you use a catalyst. So at the moment this reaction's not got a catalyst, but catalysts will lower the activation energy, so they lower the energy you need to start the reaction, which means that if we were to add a line onto this graph to show what happens to the pathway with a catalyst, it would start in the same place, but it would not go up as high, and it would still finish in the same place. So you can basically draw any line that doesn't go as high as the solid, the non-catalyzed one. However, it can't touch or overlap at any point. So for example, you couldn't do that. That wouldn't get marks because it overlaps. So you need to make sure that it starts at the exact same place, but it doesn't actually touch, and it finishes at the same place. It doesn't overlap or touch. Okay, so as far as collision theory and reaction pathways go, that is basically it. Most of it is just giving the two requirements for a successful collision and then interpreting these potential energy graphs or drawing on lines for if you use a catalyst or adding one on if there hadn't been a catalyst used. So I hope you found that helpful. If you did, please give it a like and don't forget to subscribe.